Okay, good afternoon and welcome again to the European Non-Associative Algebra Seminar. I'm happy to introduce the speaker of today, Senne Trappeniers from the Free University of Brussels. The title of his talk is The Interplay Between Skew Braces, the Young-Baxter Equation, and Hopf-Galois Structures. Please.
Okay, thank you. Well, first of all, I would like to thank the organizers for inviting me. It's always nice to, usually you can give like talks of 15 or 20 minutes in conferences, and it's always nice to have someone more time to, talk about what I do in my daily research life. So yeah, there's three main concepts and the idea is to link them together today. So of course I could start by telling you, start with the definition of a skew brace. So a skew brace or skew left brace is a triple, A plus circle, where A is a set, A plus and A circle are group structures. And for all A, B, C, and A, we have this kind of weird looking skew distributivity relation there. And if A plus is abelian, then we say that A is a brace or a left brace. Now, of course, I can introduce the definition, but I assume from like most of people in the audience, it's not clear why at all we would be interested. Maybe let's first of all look at an example, so at least show that such a structure exists. So we can obtain easy examples by starting from a group G circle. And then if we, as the first operation, either put exactly the same operation circle or the opposite operation, then we obtain skew braces. Because the condition that we get, well, it just comes down to verifying these equations here. This for the first one and this for the second one. And this is just, well, there's nothing really happening there. It's important to note that whenever I write an overline, this means that I'm taking the inverse of an element in the group given by the circle operation. As I said, it might not be clear at all why we would be interested. At least we know that these things exist, but they're just coming from groups. So what is happening here? So my main goal for today is not necessarily to tell you how people study skew braces. It's rather to in some sense explain why one would be interested in doing this, and well, moreover, just explain why I am interested in these structures and why I have been I'm doing my PhD on these structures right here. And to give a small, like a very short background story, which I will go into more detail in just a second, is the following. So it all started in, it basically started in the 90s when Drinfeld proposed to study a certain version of the Young-Baxter equation, which originally comes from physics. And he wanted to study the set-theoretic solutions of this Young-Baxter equation. And in 2006, 2007, Wolfgang Rump discovered that there was a link between involutive, non-degenerate set-theoretic solutions of the Young-Baxter equation. I will come back to all of these notions in just a second. And Jacobson radical rings. So what are Jacobson radical rings? These are rings that coincide with their own Jacobson radical. So of course, they should be non-unitary. So he found a way to produce, starting from a Jacobson radical ring, an involutive, non-degenerate set-theoretic solution. And then he thought, well, what intrinsic properties of Jacobson radical rings actually yield this solution? Is there a possibility that we can relax this definition? And this is indeed what he did. And he came up with the notion of a left brace. So Jacobson radical rings are examples of left braces, but the class of left braces is way larger than just this one. And in this case, it's not only true that one can start from a left brace and find an associated solution, but also in the other way, there's a nice way to go from solutions to left braces. Okay, so that's what happened in 2006. Then around 10 years later, in 2017, Leandro Guarnieri and Leandro Vendramin, they generalized the definition of a left brace to that of a skew left brace. And what does this mean on the side of set-theoretic solutions? Well, we can drop the word involutive. So now we're working with non-degenerate set-theoretic solutions of the Baxter equation. And once this general definition was given, a very obvious, or not obvious, but one of the first things, first alternative definitions that one can give is to see a skew left brace as a transitive subgroup of the holomorph of a group. But then Baxter noticed, and this was further explained by Byte at some point in an appendix of a paper, these transitive subgroups of the holomorph, they played a very important role already in some other field of mathematics, namely in Hopf-Galois extensions. So in this way, because this link was already there, we all of a sudden had a link between skew left braces and Hopf-Galois extensions, which at first was not obvious at all. And well, these two links here are precisely, these two connections are the one I will be talking about today. Some people in the audience might have heard about skew braces, or also in some form you can call them post groups, because there's also a link with pre-Lie algebras and also post-Lie algebras. The pre-Lie algebra connection was first described by Agata Smoktunovic, and the one with post-Lie algebras was described in a paper published in the beginning of this year by Bai, Guo, Sheng, and Tang. And Sheng also gave a seminar, well, for this same seminar here a few months ago. So I will not talk about this connection right here. I will be talking about these two right here. Okay, so let's try, well, not let's try, let's first look at this one here, which is historically the first connection to pop up. Well, this is the definition I gave you earlier. But this is the definition, but let's start by looking at something which might be more convenient, and this is the definition using one co-cycles. So what is a one co-cycle? If G and A are groups, and we have a lambda a lambda going from G to automorphisms of A, so an action of G on A by automorphisms, then a map is called a co-cycle if for all G and H in G. This well, kind of twisted property holds here. So phi of GH is phi of G times lambda G acting on phi of H. First of all, you can know that if this action is trivial, for example, we just get the usual group homomorphism. And what's the link with skew braces? Well, if you have two groups, then the following data are equivalent. So on the one hand, an action lambda of G on H and a bijective co-cycle. And on the other hand, a skew brace G plus circle such that G plus is isomorphic to A. And sorry, I should also say that the operation here on G already is circle, because otherwise this does not make sense. So both these groups show up as a multiplicative group and additive group of the skew brace here. Okay, it's in this form that they will show up in a natural way. Now, how do we go from one to the other? Just a quick sketch of what's happening here. So if we start with a skew brace A plus circle, we can define lambda A of B as minus A plus A circle B. So in some sense, this lambda measures the difference between the two operations there, because we first multiply by A in one group and then subtract A, so working in the other group. And the fact that this respects the addition easily follows from the equation, which we took as a definition, which always holds, because one can simply add minus A in the beginning of to both sides. And then here we find lambda A of B plus C, and here we find lambda A of B plus lambda A of C. Of course, one also has to prove that in this case, that lambda of A circle B is lambda A after lambda B. This I will not do, but this is the one to quickly show up. And why would this be the right definition of the action? Well, we have a circle B. One can of course, well, say we take, okay, we take plus a minus a here, but then you see all of a sudden the minus a plus a circle B is showing up here. And then we indeed find that a circle B is equal to a plus lambda a of B. So the one co-cycle condition is satisfied. Now there's no phi showing up here just because our two groups are already defined on the same set. So there's no map necessary to go from one to another. And because they're defined on the same set, well, basically take the identity, but the identity, of course, is bijective as well. So this is one direction or an idea of how to go from one direction to the other. And this lambda map will show up in, well, almost every aspect of whatever you want to study in skew-based theory. So let's look at the Yang-Baxter equation. So there's plenty of ways to introduce the Yang-Baxter equation. Historically, the Yang-Baxter equation comes from physics, but because I don't want to well, talk too much about physics, there's also a nice link coming from braid theory, which is quite a natural example. So for example, we start with the braid group Bn. So this is generated by B1 until Bn minus 1. So the braid group on n strands. What does the B1 or Bi mean in general? This means that we take the ith and the I plus 1 strands and we twist them. And what are the relations that we have in our braid group? Well, precisely, oh, sorry, that's a typo, so the one here should be an I. So precisely this right here, so if you first flip these two, then these two, and then these two once again, this is the same as starting from the first two, then the last two, and then the first two again. And this, well, I assume for everyone we've seen some knot theory, this, well, it's precisely the Reidemeister tree move that we then formulate in an algebraic way. What happens with generators which are far away from each other? Well, they just commute because twisting two strands here and then twisting two strands far away, these things commute. And okay, let's now assume that we are interested in actions of the braid group, and not just any action, but actions in some sense a natural way, I would say. So let X be a non-empty set and start with the bijection R going from X squared to itself. And then we can define Ri going from Xn to Xn as, well, basically R applied to the ith and I plus 1 place. So everything before that is just the identity, everything after it is also the identity, and then at the ith place, ith and I plus 1 place, we apply R. And the question now is when do we obtain an action? When we say, well, our Bi, which consists of twisting these two strands, like the ith and I plus 1 strand, when, if we map this to Ri, do we obtain an action? Now, the nice thing is that the commuting relation that we have, this is automatically satisfied, because if we apply R at, for example, the first two coordinates and then apply R also to the last two coordinates, these things are gonna commute. But it's the other relationship which is interesting. And one easily finds that this happens if and only if R1, R2, R1 is the same as R2, R1, R2. So we can just focus on the first three strands. This is sufficient, and if this is satisfied on the first three strands, so we can just look at X to the third, then also all the other kind of translations of it are satisfied. Okay, and it happens that, well, that actually this is precisely the definition of a set-theoretic solution to the Yang-Baxter equation. So we have a pair X, R, X in an empty set, R growing from X squared to itself, a bijective map such that this condition right here is satisfied. Then there's two important classes of solutions. There are the non-degenerate ones. So what does non-degenerate mean? This means that the sigma X and tau X, which are defined in this way here, they should be invertible. So what's especially in light of the action that we had earlier, how should one think of this? Well, in some sense, the one of the generators of your braid group acting, well, it's gonna twist the two strands. So you see the X being moved to the other side and the Y being moved to this side. So what's happening is that you're twisting the elements, but while you're twisting them, um, the X is still gonna act on the Y, and the Y, so Y is still gonna act on X. So it's not just twisting, but it's twisting, and there's also a permutation happening. So that's the way to think of this non-degenerate condition there. Involutive is easier to formulate. It just means that R square is the identity on X square. And in order to always talk about a non-degenerate set-theoretical solution to the Yang-Baxter equation, I will just call these things solutions or solutions to the Yang-Baxter equation. But from now on, whatever solution we see will be assumed to be non-degenerate. And because this might look very technical, well, I admit that in some sense it's technical, but let's look at an easier example given by Rex. So a rec is a set X together with some operation, which I will denote by triangle, growing from binary operation itself, such that left multiplication is invertible, and this operation is also self-distributive. So meaning that X triangle, Y triangle, Z is, well, it distributes over, so we have here X triangle Y acting on X triangle Z. In particular, except in very trivial cases, this is definitely not an associative operation in this case. Nonetheless, it is very useful because Rex arrives very naturally when we study colorings of knot diagrams. And what's the relation between Rex and solutions of the Yang-Baxter equation? Well, if we look at solutions of a certain kind, so we say, well, we start with any binary operation on X, denoted by triangle, then if we want, well, recall that here if you look at this form, so here on the right-hand side, we have a Y of X. Well, just assume that this Y is the identity. There's nothing happening there. Here, however, there's something happening. So once again, the Y is flipped to the side, but X is acting on it. X is changing this Y. Well, we find that this gives you a solution if and only if the operation that we have here is a rec. So it really, this actually shows that recs yield a special kind of solution of the Yang-Baxter equation, precisely those where one of the two components is, well, there's nothing really happening there, so it's just moved to the other side. And what's a natural way to construct recs? Well, or one of the most natural ways to construct a rec is starting from a group. So if we start with the group G, and then let our operation be given by a conjugation, then we can see that we obtain a rec because, well, this is H acting on K by G. And here you see that this is precisely the right-hand side, and it's just a matter of canceling G's and G minus 1s against each other, and then we find that these two things are equal. So this is a nice way to construct a rec, and then of course it's natural to ask, well, maybe all recs can be constructed in this way. So how would one go about constructing this? Well, we basically want to then construct a group where conjugation in this group, so a group generated by, well, our set X, where we have this rec structure. And what do we want? Well, we want precisely this thing right here holds. So we can force it and just say, well, take the group generated by X, and we have this relation hold here. Now it's very convenient to also look at it in this way. So we move the X minus 1 to the other side, and now we have these kind of relations that hold here. What's nice about this in particular is that you really have the associated solution showing up there, because recall that the solution of the Yang-Baxter equation associated to a rec precisely said, well, the couple xy is being sent to x triangle y comma x. So this is showing up there in the definition. And in this case, it's clear that because we defined this right here, that if we look at the canonical map going from X to the rec associated to the structure group, that is the homomorphism of recs. So if this would be injective, then in some sense we show that every solution at least embeds into a solution. Every rec at least embeds into a rec coming from a group. However, it's not always the case that this is injective. For example, well, the easiest example I could think of was taking n to be an integer, then let x be the set z modulo n, and K triangle L will be defined as L plus 1. So whatever element we have acting on the left side, we just add 1. So we have like just a cyclic permutation of our sets happening there. And in the GX, so recall this is the one defined here in this way. This is a nice way in this case to think about it. So this means that xy should be equal to y plus 1x. So recall that this plus 1 does not mean anything in the group here. It's just the cyclic permutation happening there. If we once again apply the relation, one of the defining relations, then we find that, well, we can move the y plus 1 to the other side, x plus 1 to the left side, but then we add 1. If we do this often enough, at some point we find the following, that this is equal to x plus n minus 1 times y plus n. But recall that we're working modulo n. So, well, this is just y. And y here means, of course, we're working in a group, that x should be equal to x plus n minus 1. But once again, we're working modulo n, so this is just x minus 1. So we find that x should be equal to x minus 1. Well, of course, this is somewhat complicated sometimes in skew theory, but the x's I'm talking about here are seen as generators of this group, no longer necessarily in this set. So we find that the generator x is the same as the generator x minus 1, and so forth. So all the generators are identified, and we just end up with, well, the free group on one element, which is not very interesting. Still, this group is useful because, for example, one can easily check that this construction is functorial, and in this way we obtain a left adjoint to the function functor associating to a group its associated track. Because, well, this makes sense to see this as this is in some sense a forgetful functor. We only we take a group, and then here we only remember how adjunction conjugation works. So being left adjoint to the forgetful functor means that it makes sense to think of this group as the free group generated by our rec. Okay, so this is an important idea to keep in mind. Now let's see how we can do a similar thing for solutions of the Yang-Baxter equation. So in this exactly the same fashion as before, we start with the solution XR, and we add the following relations. So for any x and y, x times y should be equal to, well, this product right here, but recall that this is just the image of, basically just the image of the pair xy. This generalizes what we did before for recs. And one can once again verify that we have a functor, but it's not clear whether this one has a whether this one has a right adjoint, not because we want this to be left adjoint. So it's not clear whether this has a right adjoint, and it feels like having just a group structure is not sufficient. Why would I say this? Well, here, if we look in this case, you see that, well, of course, we move this x to the other side, and we find, well, our rec operation should be given by this formula right here, which is completely independent of the rec structure that we have there. On the other hand, here there's two things happening. You have both the sigma x's and the tau y's, So it's kind of like you're trying to solve an equation with two variables, but you only have one equation. So we want some more information because otherwise we can never isolate a certain sigma x and tau y. Now, keep in mind that this is just the intuition behind it. But it feels like there's something missing here in this case. How can we find this, fill this gap? Well, we see in just a second. On the other hand, just to show that the structure group in itself is really convenient, one can look at the following lemma. So this view write the solution R as, well, with the usual notation, which we have done in the last 3 slides. Then if explicitly write out the Yang-Baxter equation, of also called the braid equation in this case, and look at the 3 different components that we have, now we find the following 3 conditions. The third one we will ignore because it's a very technical and awful condition to verify usually. On the other hand, if we look at the first one, so saying that sigma x after sigma y applied to z should look like sigma of sigma x of y applied after sigma of tau y x. But once again, we see the original solution R showing up because xy is mapped to this pair right here. And if you look back at the definition of the structure group, this means precisely that if we can let the group GXR act on X. How do we let it act? Well, we let the generator act, generator X acts by sigma X. And because this condition is precisely this condition, this gives a well-defined left action of GXR on X. Then if we look at this is almost the same thing happening here, although here the 2 components are kind of switched. But in this case, we find that the tau x can be used to obtain a right action of GXR on X. So we have a left and a right action from GXR on X, and it's mainly the one defined by the sigmas, which will be useful. So the action by the sigmas will be denoted by lambda. So recall lambda is an action of GXR on X. Okay, so as I said, it seemed like we were missing some information in order to find a right adjoint to this functor that we just defined. So let's try to add some of this information. And main observation here is that starting from a solution, we can always associate a rec to the solution. So we start from a solution, and there's this nice graphical way of representing this action of the braid group that I talked about before. In this case, we can even look at the braid group on 2 strands, which is, well, just Z. So if we start from a pair YX, we apply R once, we get this here. If we then once again apply R, we end up with something. And I don't care what's in the right hand side. So now just looking at what's happening here on the left, we will define a new operation, binary operation from X by saying, well, this thing, so sigma y of X acting on Y, is precisely this thing. So this is by definition. Now, it's not very convenient to have this sigma y of X there, but of course the sigma y's are invertible, so we can see that this is just equivalent to this right here. And well, one can prove that it's not a coincidence I'm using the same notation, that what we obtain is a rack. And is there a connection with the previous, well, the original solution we started from? Yeah, there is, because the sigma axis, they yield rack automorphisms. So we find a bijection which respects this operation. So in particular, recall that this lambda was at first just an action of GXR on the set X, but, well, we know that the set X with this operation there is being respected by the sigmas. Also, actually, the lambda action here is an action on automorphisms of this rack. Now, the first thing one thing we saw about racks is that we can always, well, because it's in particular a solution of the Baxter equation, we can always look at the structure group of this rack. And so the rack here is called the derived solution of the original solution. The structure group of this rack, we will denote it by AXR and plus. This is more convenient to use the plus here. And we call this the derived structure group of our solution XR. So recall this is just the definition that we had before, except now we're not using juxtaposition, we're just using the plus here. And recall we had this action here, so GXR on this rack, but because our construction here is functorial, we quite easily find that we also have an action on the derived structure group. Okay, now we're really close to the definition. Well, it seems that the definition of a one co-cycle is showing up there. And indeed, so we have an action here of GXR circle on the automorphism group of, on AXR by automorphisms. And, the authors disappeared here, but this is mainly by Ittinghoff, Schettler, and Soloviev. They proved that there exists a unique bijective one co-cycle, so from this group to this group, such that, well, recall that this group is generated by the set X. This group is also generated by a set X. So this one co-cycle satisfies that f X is X. So generators are mapped to themselves. Okay, but we started with saying that the bijective one co-cycle is actually the same as a skew brace. So we can, instead of considering this bijective one co-cycle, we can transfer in some sense the group structure of AXR to GXR, and we find a skew brace structure on GXR. And once again here we can easily check that this is functorial. But the problem that we had earlier where we said that there was like not enough information to find a functor going from group to solution of the Baxter equation in as much generality as we wanted. But this is in some sense solved because we have added more information, because we also have another group operation, which in general is not going to coincide with the original one. Now let's see what adjoint functor. So we're searching, let's try to find the right adjoint to this functor. In light of the previous construction, there's two assumptions that one could put. So first of all, recall that the sigmas were given, the sigmas were used to obtain the lambda action. So also the other way it makes sense that this works. So if we start from a skew brace, recall that from a skew brace, we can always define a lambda action by this lambda A of B is minus A plus A circle B. So we have this action for any skew brace, and we want that the associated solution on the first component, at least, the sigma is actually going to be given to a lambda in this case. Whatever happens on the second component here, we don't care. But also, coming from a solution to the structure group, this condition right here was essential. So we said that, well, going from one side to the other, we said, well, if this pair is mapped to this pair, then this relation should hold. And now we're kind of trying to do the opposite, or at least we're forcing this, and we're saying, well, if this here holds, then also, well, these things should be equal. But with these two things, well, recall that a circle is a group. So having this condition right here, and we know what the left component looks like. Well, if we want the product of these two to be equal to the product of A and B, well, this is the way to do it. We just say, well, we want to end up with A and B. We put lambda A of B inverse there, and then once we multiply these two, we get a circle B. Okay, so these are things following from the kind of natural assumptions that we had. Of course, it's not clear at first whether this is a solution of the Baxter equation, but it turns out to be. And moreover, it does satisfy the property that we want. So it's a functor, and also it's going to be right adjoint to the functor associating to every solution its structure skew brace. So this is a very nice way to really show that solutions of the Baxter equation, or at least the non-degenerate ones, and skew braces, they are inherently connected. Because, well, we can go from one to the other, and the skew braces precisely contain enough information to find interesting solutions to the Baxter equation. So this is a starting point. Now, on the other hand, one can easily see that the structure groups or the structure skew braces that we obtain, even if one starts from a finite solution, we will end up with something which is infinite. Which, for example, when we want to use a computer to compute things, this might be a problem. In practice, however, there's always another certain quotient. So quotient as a skew brace. So there's another other skew brace, which is called the permutation skew brace, which still captures the most essential features of XR. And it's usually, well, not usually, but like 50% of the cases, people tend to study this. This skew brace there. The main reason being that if XR, so if the set X is finite, then also this permutation skew brace is going to be finite. A downside, one of the downsides to this is that this construction is no longer functorial. It does preserve homomorphisms in, well, when there's surjective, for example, but it's not true that any homomorphism in the side of solutions is going to yield a homomorphism in the side of permutation skew braces. And so let me just to end this part about the solutions of the Baxter equation, let me mention two important results. The first of all, the first was proved by Baxter, Sedo, and Jespers, and then generalized by Baxter 2 years later, and says that if we're giving a skew brace, then it's possible to construct in a somewhat algorithmic way all solutions XR such that their permutation skew brace is isomorphic to the skew brace. So in some sense, well, this is in theory, of course, but in some sense, if someday we were able to classify all skew braces, which we don't hope to do because it would be the same as saying classify all groups. There's no way to start such a thing. But if we theoretically would know what all skew braces look like, we would know what all solutions of the Yang-Baxter equation look like. So that's one nice theoretical result. And then, of course, a very natural question is how certain properties of solutions translate to properties of the associated, well, either structure skew brace or permutation skew brace. And one natural notion, for example, is having a finite multi-permutation level, and it was proved that if you have a solution XR with finite multi-permutation level, which I will not give a definition, but think of it as being that one can take retracts of elements acting in the same way, and if we take the retracts sufficient amount of times, we get a trivial solution. So this is equivalent to its permutation skew brace having a finite Sokal series. I might have well have said that also this means that the structure skew brace has a finite Sokal series. But once again, this is more convenient usually when working with finite solutions. Okay, so let me conclude the part about solution of the Yang-Baxter equation there, and let's say something about another nice connection, and the one which is the one with Hopf-Galois structures. So before doing this, so we're making a big switch from combinatorial stuff to well, number theory basically. So recall that let's do some stuff in the classical setting. So let's start with a finite Galois extension L over K with Galois group G. Then it's natural to consider the group algebra KG. We can, of course, look at it with its canonical K-Hopf algebra structure. And we can let this Hopf algebra act on L by, we call this action, we denote it by star, by saying G star L is G applied in L. This makes L into an H module algebra. What does this mean in this case? Well, because our KG is generated by group-like elements, this just means that the group-like elements act by automorphism on L, but this is by definition true. And then there's a natural map to consider going from L tensor H, so tensoring over K, to the K linear endomorphisms of L. So at this point, we're actually just looking at L as a K vector space. And tensor X H is going to be mapped to the endomorphism, which maps an element Y to, well, here we have Y being acted upon by H and then multiplied by X. And well, a very classical result in Galois theory states that the automorphisms of L over K are L linearly independent. But what does this mean in this case? Well, first of all, note that the K dimension here and here, they are the same. So in order, if you want this thing right here to be bijective, it's sufficient to say that it's injective. But injectivity means precisely that all of the group-like elements here, so all the elements in the Galois group, they should be L linearly independent. So in this case, from this classical result, we find that this map right here is a bijection. And the main idea behind Hopf-Galois structures is to take this behavior as a definition of you want the object to behave like this. So what is a Hopf-Galois structure? Once again, we start with this can be formulated in a more general way, but we just look at Galois extensions for the time being. So once again, we start with a finite Galois extension with Galois group G, and a Hopf-Galois structure on L over K consists of a K-Hopf algebra H, an action star of H on L such that L is an H module algebra, and this map that we had before, which we can still define for any Hopf algebra H acting on L. This right here should be bijective. And so what we saw on the first slide was basically that for any Galois extension, we can always let H be the group algebra on G. And then from classical Galois theory, we find what we call the classical Hopf-Galois structure. Of course, one would hope that there's more Hopf-Galois structures here, because otherwise it does not make sense. It does not make too much sense to generalize the definition. And indeed, there are more of these Hopf-Galois structures, and there's a very nice way to find all of them, and it's the following. So what I proved together with Lorenzo Stefanello, building up on results by Bayet, Childs, and some other big names in Hopf-Galois theory, we found that there exists a bijection between Hopf-Galois structures on L over K and operations plus, such that if we put this plus operation on our Galois group, which we will now denote by circle, this makes it into a skew brace. And in general, well, I don't have like exact numbers, but in general, for any given, there's only a small family, it's still an infant family. There's quite a small family of groups which do not have non-trivial skew brace structures. So in general, we will almost always be able to find such an operation here, meaning that non-trivial one, meaning that here we have an interesting, or hopefully an interesting Hopf-Galois structure. Now, how does this tie in with the start of my story, where I started telling you about the classical Hopf-Galois structure? Well, let's try to think of the easiest skew brace that one can consider, and is actually the skew brace that we considered in the second slide. So we start with the finite Galois extension, and no, sorry, let me first tell something about the general case and then look at the specific case. So we start with a Galois extension, with Galois group G circle, and we are given a skew brace structure. So we are given this plus. This time, instead of considering the K Hopf algebra KG, we look at the group algebra of G plus over L. So L is our bigger field. In the classical example, we start with a smaller field. Now, G circle acts on L via, well, Galois action, but also acts on G plus because recall this is a skew brace, and skew brace, we always have this lambda action. So combining these two, we have a natural action of G circle on LG plus, so in coefficients by Galois action, on group-like elements by this lambda action. And without being too precise here in this case, this respects the Hopf algebra structure in a certain sense. Now, what we can do is restrict to the fixed points of this action. And because the action respected the Hopf algebra structure in a nice way, actually what we get, these fixed points, they have the natural structure of a K-Hopf algebra. And now in this K-Hopf algebra, where the elements are still, of course, looking like linear combinations of elements in G with coefficients in L, an element we can let it act on L by, well, the somewhat natural way to do it. So we make it linear, we make it L linear, and we let an element G, so recall G is contained in the Galois group. It's living in the Galois group of L over K. We let it act by, well, applying it to this element. And what we get is a Hopf Galois extension. Now, it should be noted that it's impossible in general to try to define this action right here before taking the fixed points. Because recall, in general, it's G circle acting on our Galois extension. It's definitely not G plus acting there. So it's somewhat surprising that what we define here, although the ring multiplication here is given by this plus operation, it still works and still makes sense to that this gives you an action. Okay, so this might look complicated, but now we can look at what this looks like in concrete example. So if we look at the easiest possible skew brace that one can take, which is just the one with both operations, well, the same. Then the lambda map, so recall lambda G of H in general is minus G plus G circle H, but plus and circle coincide in this case. So this inverse of G and G is just going to cancel out, and we find that actually our action right here is trivial, which is to be expected because this is, well, somewhat the easiest easiest skew brace we can think of. But now that this means that the action of G, we still have it acting on L with the usual Galois action, but on the group-like elements here, it's not going to do anything. So one can easily verify that the elements living in the fix here, these are just the well, all the ones where the coefficients are living in K. And now the action of K, which given by this formula right here on L, is just the canonical one that we saw earlier. So in this case, starting from the trivial skew brace structure, we find the classical Galois extension again. And I don't know, do I have some more time left? Because I had some more slides, but I can skip them. I don't know how many.
You have 11 minutes. Again.
Okay. So then I can safely tell you something more, because of course the strength of Galois theory is not only looking at the automorphism group, but mainly once we want to study intermediate extensions, that we have this correspondence, or the Galois correspondence, with the subgroups of the Galois group. And of course, it makes sense to ask whether some similar thing is happening right here. And there is indeed. So a well-known result in Hopf-Galois theory is that if we have a Hopf-Galois structure H star on L over K, then there's an injective map mapping a K Hopf subalgebra of H to an intermediate field of L over K. How do we do this? Well, we look at the fixed fields. So this is not very, this is somewhat a natural thing to do, because if we once again think about the classical structure, then K Hopf subalgebras of the group algebra are just the group algebras over subgroups, and then the fixed field, the fixed field here in the Hopf algebraic sense just comes down to the fixed fields of this, the subgroup that we take here. And so the same idea works for Hopf-Galois extensions, although it should be noted that this map is just injective. So it's no longer a one-to-one, like one-to-one correspondence, or like bijective correspondence. We only have injectivity. And this is still very useful, although it's not necessarily surjective, and this we'll call the Hopf-Galois correspondence. Now the question would be, of course, whether our translation between Hopf-Galois structures on L over K and skew-brace structures over the Galois group, if they're, this Hopf-Galois correspondence can also be formulated starting from just a skew-brace, and we can, in some sense, ignore the Hopf-Galois structure there. And then, of course, one should ask, well, which substructures of a skew-brace might be important? Well, there's plenty of them that might be important, but one of the earliest substructures of skew braces to show up are left ideals. What's a left ideal? Well, starting from a skew brace A plus circle, we say the left ideal is a subgroup of A plus, such that it's fixed under the lambda action, so not pointwise fixed, but mapped to itself. So there's a natural notion. It should be noted that from this, it follows immediately that this is not just a subgroup of A plus, but it also gives you a subgroup of A circle, which is important in what we do here, because we now find a bijection between left ideals of our associated skew brace and K Hopf subalgebras of H. So the left ideals in this case are precisely the ones that we're most interested in. And because recall that these objects right here, they appeared in the Hopf-Galois correspondence. Well, what happens if we apply this bijection here? Well, we find that the Hopf-Galois correspondence basically says that any left ideal of G plus of a skew brace G plus circle, we can associate as an intermediate field of L over K. How do we do this? Once again, in the way that we would expect it, because as I said, left ideals are in particular subgroups of the circle group, but the circle group in this case is the Galois group. So we're gonna map such a subgroup of the automorphism group to its fixed field. So in this sense, you once again see the classical Galois connection correspondence showing up. So that was everything I wanted to talk about today. So I'm sorry for those who were maybe expecting more concrete stuff on skew braces, but at least I hope that I convinced some of you that skew braces, although this weird skew distributive definition there might be a very artificial looking thing, that skew braces are, they have their place in mathematics, and they occupy this weird place in between set-theoretic solutions on the one hand, Hopf-Galois structure on the other hand, post-Lie algebras. So seemingly unrelated structures, they seem to be linked and twined using skew braces. So that's my point I wanted to make today, and thank you for your attention.
Okay, thanks, Sen, for your interesting talk. Are there any questions? Please, Marcia. Okay. There is some question on the chat.
Mm-hmm.
Could you relate these topics to Boolean algebras?
Well, then my first question would be, what is a Boolean algebra precisely? I can quickly try to Google it in order to, but I don't know precisely what, there's an unwritten. Yeah, no, because I know what the Boolean ring is, but I don't think I think we're talking about different notions.
So, Florin, do you want to expand your comment? Or? Okay, research topics. So, by Boolean algebra, you mean an algebra which is Boolean as a ring?
Future collaboration. Okay, well, I will gladly think about it. Once I have the definition, I can definitely think about it. There might be, well, there might be a relation. If these things are Jacobson radical rings, for example, then yeah, sure, there is an obvious link, but I have no idea in general. I would have to, well, see the definition and think about it for a second. But of course, you can contact me through mail if you have a question, and I can definitely elaborate on this.
So, Florin, do you want to elaborate a little bit your question, or it's okay for you? Okay, no reaction. So, any other questions? Comments or remarks? Okay. If not, let's thank the speaker again. And we will resume on next Monday at the usual time. Bye-bye. Goodbye, everybody.